that on Canvas, there's already a video. There's already videos that are posted on Canvas. Those videos were from spring quarter. But you know, I'm making new videos this quarter, and I'll replace those old videos with the new videos. Okay. Okay, but the first thing I'd like to ask you is, what did I just write on the board?
Numbers.
Very good.
1, 2, 3, 4.
You guys are too smart for me. But if you asked your parents, let's say, assuming they're not computer engineers or electrical engineers, maybe, what do you think most people would say I just wrote on the board?
123.
Right, most people would think, well, 123, right? Because we're all programmed to be base 10, right? That when we look at these characters that are numbers, our brains think base 10. And, you know, you don't even probably even are conscious of this anymore. It's probably part of your subconscious because, you know, you're so used to it. But there was a time when you first learned about numbers that you were told that if there's not a point here explicitly, right, what do we call this point? There's no point. Well, if it's not there explicitly, it's implied, right? And then right to the left of that decimal point, this is the ones column, right? And then the next column over, that's the tens column. And then the next column over is the hundreds column, right? And so on. And, you know, to the right of the decimal point, you learn that this is the tenths, right? This is the 100ths, and so on, right? But you don't even think of that anymore, right? Because it's so ingrained, right? Because it was so long ago that you first learned about base 10, and you've used it so much, you don't even really think about it anymore. Now, how many characters, the number of characters, how many characters do we have in base 10?
10.
Right, 10, right? Because it's 0 through 9, right? Because 0 is a character, right? So we have 10 characters, right? 0 through 9. Well, this that you already know about base 10 applies to any base. All bases have the same number of characters as the base. All bases have these columns with certain values. Okay. You know, you probably learned about the ones and the tens and the hundreds and the tenths and the 100ths columns. You know, you probably learned that back, I don't know, when you first learned about numbers, probably really early grade school, right? Probably like first, second grade, whatever it is. But then, you know, a little later in your math, you learn about powers, right? And then you learn about how, you know, this ones column is the 10 to the 0, right? Because any number to a power of 0 is 1, right? You learn that in math. I don't know, when do you learn that? You probably don't learn that till a little later on, right? But then you also learn that, you know, this is a 10 to the 1, this is 10 to the 2, this is 10 to the -1, this is 10 to the -2. Well, these powers, again, it's the same concept in any base. And in digital design, there are certain bases that we commonly use. And one of those is base 2. Okay, which is binary. We call it binary. So how many characters do we have in base 2?
2.
Right, 2. And what are they?
1, 0, 0.
0, 1. Because you gotta have 0 in any base, right? Because no matter what base you're talking about, you could have like nothing, right? So you gotta have 0 in every base. So yeah, base 2 has 2 characters, 0 and 1. And then the columns in base 2, well, their words, so their values are 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and so on. And then there's also a point. Now, in any other base other than base 10, this point is not called a decimal point, right? Because decimal stands for base 10. In other bases, this is called a radix point. radix. Okay, radix is just another word for base. Okay, so, just like you have 10 to the 0, 10 to the 1, 10 to the 2, and so on in base 10, in base 2, you have 2 to the 0, 2 to the 1, 2 to the 2, and so on. In base 10, you have 10 to the minus 1, 10 to the minus 2, right on the other side of the decimal point. In base 2, on the other side of the radix point, you have 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, and so on. Okay? So in base 2, you still have a ones column, right? I mean, every base is going to have a ones column because, again, any number to the 0th power is 1. But then 2 to the 1, this is the 2's column. 2 to the 2, this is the 4's column. 2 to the 3, that's the 8's column. 2 to the 16, that's the 16's column. Okay, and so on. Go 32, 64, 128, 256, 512, 1024, 2048, and on and on. See, just like in base 10, as you go from column to column, there's a factor of 10. In base 2, as you go column to column, there's a factor of 2. Okay? 2 to the minus 1, how many halves? 2 to the minus 2, how many quarters? 2 to the minus 8, how many eighths? Okay, so can you see how conceptually it's the same as what you learned a long time ago, right? The only thing that's different is the base number. Right? Okay, another popular base in digital, although this is not as popular as binary, and another one that we're going to talk about after this next base, that's base 8, which is called octal. So how many characters in base 8? 8. And what are those characters?
0 through 7.
0 through 7. Yeah. 0 through 7. Okay, so like in any base, there's this point, again, we call it a radix point in base 8. But it's the same idea that you're going to have an 8 to the 0 column, an 8 to the 1 column, an 8 to the 2 column, 8 to the minus 1, 8 to the minus 2, and so on. So here's your ones column, here's your eights column. What column is this word? 64s, right? Because 8 squared. 1/8 column. What's this column? 1/64 column. Okay. Yeah, I should have mentioned this right at the very beginning, but if you ever have questions about anything I'm talking about, just yell it out. Okay, you don't have to wait to the end. I mean, I take questions at any time. Okay. All right, another base that's very popular. In fact, this base along with base 2 are the two most popular bases other than base 10 that we use in this class and that you'll use in other digital classes. And that's base 16. Anyone know what base 16 is called? Hex. Hexadecimal or hex. Okay, so hexadecimal or hex. So how many characters in base 16?
16.
Do I have any Jeopardy fans? Anyone watch Jeopardy? That seems to be a show that young people don't watch it. Has anyone heard of Jeopardy? Oh, okay, you heard of Jeopardy, you just don't watch it, right?
Yeah.
But if you watch Jeopardy, sometimes they have this category, stupid answers to stupid questions, and the answer is in the question, right? So you see, that could be one of those questions, right? How many characters in base 16? 16, right? Because the answer is right in the question.
Will that be on the midterm?
Base 16 will, now I don't know about that specific question, but base 16 definitely will be on the midterm. You'll see that base 16 is very important for this class. Okay, so we need 16 characters. Does anyone know how we do the 16 characters in hexadecimal?
It's 0 through 9 and then ABC. Yeah.
Exactly, yeah. We go 0 through 9.
Sure.
Right, so that's 10 of them, just like in base 10. But then we start using letters. A equals 10, B equals 11, C equals 12. D equals 13. E equals 14. And F equals 15. Yeah, by the way, another thing, like when I'm lecturing up here, I tend to always start on this side of the board and work my way to the right side. So if you're way over there and you're having a hard time seeing what I'm writing, you know, feel free to move up. You can move up to this table or just bring your chair and laptop so you can see better. It's not like you're anchored to your table. You can go wherever you need to go. Okay. Okay, so like I said, of these bases, oh, well, one thing we forgot here is the value of the column. So again, same idea as what we've done before. In base 16, you're going to have a radix point, and then you're going to have a 16 to the 0 just to the left of that radix point, 16 to the 1, 16 squared, 16 cubed. And again, on the other side, you're going to have 16 to the minus 1, 16 to the minus 2, and so on. All right, so you got a ones column, a 16s column, 16 squared. You know what 16 squared is? Yeah, 256 column. Does anyone know 16 cubed?
That's 28.
I don't think so. I think it's 4,096, but you could do that on your calculator. I mean, eventually you'll do this so much that you'll have it memorized. Okay, but you could always plug it in your calculator. Okay, so again, of these bases, the most important for us, base 2 and base 16. Octal sometimes comes up, you know, and on the activity, I think I have an octal question, but in practice, base 2 and base 16 are the most popular other than base 10 that you already know. Okay? Okay, so, you know, this is basically what I wanted to talk about as far as number bases. The next thing to go over is base conversion, okay, how we convert between some of these popular bases used in digital. But before I move on to base conversion, do you have any questions about anything up to this point?
What's the radix?
Oh, radix point, it's just in bases other than base 10, because in base 10, we call this point that separates the whole values from the fractional values. You know, we call it a decimal point because decimal is just another word for base 10. Okay, but yeah, if we've got a base other than base 10, we don't call it decimal point because it's not base 10. So they just call it radix point. And radix just means base. Just another word for base. That's all. Okay. Any other questions? All right, so let's move on to base conversion. Now, by the way, you'll notice I put in red move camera. The way the camera is positioned right now, the view of the board is right about here. So I put this here because I have a habit of not moving the camera, okay, when I need to. So I mention that because if I start writing over here and you haven't seen me move that camera, please tell me. All right, don't be shy. Just say, Gary, move the camera. Okay. All right, but let's do base conversion. And first, let's convert from base 2 to base 10. Okay, this is probably one of the most common conversions that you need to do. So someone give me a base 2 number. Just give me a string of ones and zeros.
0, 1, 1, 0.
Okay, 0, 1, 0, 0, 1, 0. Okay, some more. Now, actually, this reminds me to tell you that in base 10, another word for each of these characters, you know, numbers is digits, right? You've heard that word, right? Digit. In base 2, another word for these zeros and ones is bits. Okay, because so in binary, we call the zeros and ones, we call them bits. You know, this is like bit 0, bit 1, bit 0. Okay. Okay, but give me some more here, more than 3. What do you want next?
1, 1.
1, 1. How about a few more?
0, 1, 1, 1.
Okay, that's good. And then we'll put the radix point here, and we'll put I don't know, we'll put like a 101 on this side of the radix point. Okay? So we want to take this base 2 number. Now, another thing that you'll see in this class is that after some number, whatever base is written down, you'll see a little subscript. And that little subscript explicitly identifies what base that is. Right? Because this could also be a base 10 number, right? That's 0, 1 or in base 10. Okay, so the little subscript is like a way to explicitly identify what the base of that number is. Okay? All right, well, the way that I would convert this base 2 number into base 10 is I would just use my knowledge of what these bit values are based on the column. So just to the left of the radix point in base 2, that's the 1s column. Then comes the 2s, then the 4s, then the 8s, then the 16s, then the 32s, then the 64s, then the 128s. Okay, and over here, the halves, the quarters, the 8s. And wherever there's a 1, you're going to add that to your base 10. Wherever there's a 0, well, you don't have that value in your base 10. Okay, so I just look at the bits that are 1. So this is the 1 bit. So I'm going to add a 1 with a 2. Oops. So we got a 1, we got a 2, we got an 8, we got a 16, and we got a 64. Also, we have a half, and we have an 8. So you see, I'm just taking the values where the 1s are. The 1s mean we have that value. The 0 means we don't have that value. Does that make sense? Okay, so did I get this right? Oh, by the way, when I'm doing this, if I make a mistake, again, shout it out. Okay? I don't make mistakes on purpose, but I do make mistakes. So if you see that I make a mistake, don't keep it to yourself, because there's probably other people that saw it too and aren't saying anything. Okay, better to tell me when I make the mistake as opposed to 10 minutes later. Okay, all right, but I think I got all the 1s here. So now we just got to add them up, right? So what we got 11, 27. That's going to be 91. So 91 and 5/8. I did this right. Right, you could write that as 91.625, right? And that's base 10. But you see, I put a little separate 10 just to explicitly show that that's base 10. So, any questions on this example? Does anyone want me to do another example? Or, because if you get a different string of 0s and 1s, it's the same concept, right? It's just, you're likely to have, different values that are 1, but we just add it up the same way. Okay. Okay, so everybody's okay. Does anyone want to see another example of base 2 to base 10?
Does it matter what side you start counting from?
Oh, no. Yeah, I could have added these in any direction and get this. So sure. Yeah. I mean, usually, I don't know. I think most people usually start with the whole values and then do the fractions, but yeah, it doesn't matter which one you do first. Any other questions? Okay, let's go the other way. Okay, let's go from base 10 to base 2. Okay, so base 10 to base 2. All right, so give me a base 10 number. Don't give me something real crazy. Give me something like in the tens of thousands.
13,725.
13,700 and what?
25.
25. Okay, good. Okay, so 13,725. We want to take that and make it base 2. Now, there are different ways to do this. And, if in your high school or whatever school you were at before you came to Cal Poly, if you did this base 10 to base 2 conversion, you might have used a different method of what I'm going to show you, right? Because there's different algorithms out there, okay? But I'm going to show you the way I would do it based on what a column is worth. Okay, see, what I would do is I would start with the ones column, and then just write the columns until I get to a column that's more than this value. So you see ones, fours, or excuse me, ones, twos, fours, eights, 16s, 32s. Hopefully I don't have the space here. I probably should have started over. Let's start further over so I don't run out of space over there. So yeah, ones, twos, fours, eights, 16s, 32s, 64s, 128s, 256s, 512s, 1024s, 2048s. Let's see, then it's what, 496s. And then it's 8 192s. And then I know that when I double this, I'm gonna be more than this, right? So it's 16,000 something, but I'm not gonna bother writing it because whatever would be here would be a 0, right? Because this value is bigger than the base 10 number that we're trying to convert. Does everybody get that? So you see, you just write out these columns until you get to a column that's more than the base 10 number. That's when you stop. And then you just ask yourself, you start with the largest number and you just say, well, are there any 8 192s in 13,725? And clearly, yes, there is. Right? There's an 8192 in 13,725. So now we just subtract that. Right? We subtract that 8192 from the 13,725. So let's see, we're going to have, this is going to be 5,000 here. And then 192 from 725. If this was 200, it'd be 525, but it's 8 less. So it'd be 532, right? I do that right. Again, if I make a mistake, let me know. I think that's right. Is that right? 1372 minus 8192, is that 5532? Click on the calculator.
33.
Oh, 30, oh, right, 5 minus 2. See, I told you I make mistakes. You gotta watch out. You gotta watch it. All right, is that right?
Yeah,
Okay.
that's correct.
All right, so now we got 5533. Is there a 4,096 and 5533? Sure is, right? So that would be a 1. So now minus 4,096. Let's see, that's gonna be 533 plus 4, right? That'd be 537.
430. So it's,
Oh, 4.
I got 1437.
That's what I got too.
5533 minus 4, if that was 4,100. Oh, I forgot about this over here, didn't I? All right, so yeah, it's 1437, right? Yeah. I can make mistakes. Okay, 1437, is there a 2048 in 1437?
Nope.
No. So that would be a 0. Is there 1024 in 1437?
Yes.
Sure is. That would be a 1. Minus 1024, that would be 413. Did I get that one right?
Yep.
All right. I'm 50% at this point, right? All right, so we got 413. There's no 512 in 413, so that would be 0. Okay, there's a 256 in 413. All right, so 256 would be a 1. Let's see, and that'd be 157.
Yep.
Thanks. All right, then we look, is there a 128 in 157? Yes, there is. So minus 128. That will leave us with what, 29? Is there a 64 and 29? No. Is there a 32 and 29? No. There is a 16 and 29, no? So minus 16. 1. Okay, there's an 8 and 13. And then, you know, we'd have a 4 and a 1, right, for the 5. Minus 4 and minus 1, right? So you just keep doing this until you get to 0. Okay, so 13,725 in base 10 is 1 1 0 1 0 1 1 0 0 1 1 1 0 1 in base 2. Okay. Now, like I said, there's other ways to do base 10 to base 2 conversion. Like there's an algorithm where you take the base 10 number and you keep dividing by 2. And if there's a remainder, that means the bit is a 1. There's no remainder, it means the bid is a zero. Has anyone heard that? Yeah, some people do it, and you know, if that's the way you want to convert from base 10 to base 2, that's fine. Okay, I'm not saying this is the best way to do it, I'm just saying this is how I like to do it because it just goes back to something I already know. Yeah, that's why I think it's. Okay. So any questions on base 10 to base 2 before we move on to the next conversion? No questions? Okay, let's do. See, let's do the next one I have here. Let's do base 16 to base 10. Base 16 to base 10. Okay, so give me a 4-character hexadecimal number that has some letters. Doesn't have to be all letters, but include some letters, some valid letters.
E3, 7, A.
Okay, and then we'll put a radix point and we'll put a C. Okay, so this is base 16. Okay, and I want to go to base 10. Well, again, it's the same idea. Put the values for the columns. This is the 16 to the 0, so that's the ones column. This is the 16 to the 1, so that's the 16s column. This is 16 squared, so this is the 256 column. This is 16 cubed, so I'm pretty sure that's the 4096 column, but someone check, what's 256 times 16, is it 4096? I'm pretty sure it is.
48.
Yeah, because I think the next one is the 65,535 or whatever. Okay, and then this would be the 16th column. Right, 16 to the minus 1 to 16th. All right, so now to go to base 10, well, what number does E correspond to? 14, right? Remember, you go 0 through 9, and then you start using letters once you get to 10, right? So A is 10, B 11, C is 12, B is 13, E is 14, F is 15. Is G part of base 16?
No.
No, because once we get to F, that's 16 characters. The 0 counts as a character. That's probably the most common error people make. You know, 0 doesn't get the respect that it deserves, right? People think because it's 0, it doesn't count. You know, so sometimes you don't count it as a character, and then you end up with one more character than what you really have. So just watch out for that. All right, so yeah, so E is 14. So we're going to go 14 times 4096. So that's going to be what? 40,960 plus 4 times 4,096, whatever that is. Does anyone have a calculator? I'm just too lazy to do that in my head.
57,344.
You said 57,344, you said?
Yes.
All right, great, thank you. All right, then we take 3 times 256. That would be 750 plus 18, right? So 768. If I did my math right.
68, yeah.
Okay. Then we got 7 16s. That would be what? 112? Yeah, so 112. And then we have 10 ones. Right? Because A is in the ones column, so that's 10. And then we have, oh, what's C in hexadecimal? Yeah. So you'll probably start thinking like this too. Anytime I'm looking at a letter, usually I just remember A is 10, and then I just in my head count up from that. A is 10, B is 11, C is 20. So we're gonna have 12 times a 16th, which is gonna be 3/4, right? 12 over 16, 3/4. So now we just got to add these up. So let's see, we add these two, we're going to get what? We're going to get 58,112, I think. Is that right? 44 plus 68. Is that right? 58,112? I think that's right. You want to check on the calculator?
Yeah, I got that.
You got that? Okay. And then we add one. Oh, that's kind of convenient, right? We're adding 112 to 112 here. So that's 58,000. 224. I'm sure the person that picked that number had that ahead of time. He knew it was. Oh, wait, maybe I'm confusing people with this. This is just like a binary, it's not like a 7. Okay, then we add 10 to this, so 58,234, and then you just add a quarter, so 58,234.75. That's what our base 10 number would be. Or E37A radix point C in hexadecimal. It's that base 10. So any questions? So everybody good so far? Okay, we got one more, I think fairly straightforward example, and then we're gonna get a little crazy after that, right? So. All right, but we want to go the other way. We want to go from base 10 to base 16 also. So base 10. Oops, base 16. All right, so give me a base 10 number again, not something real crazy, but you know, maybe in the tens of thousands, something like that.
16,076.
60,076. All right, that sounds like his number. Okay, we want to go to base 6. So again, it's the same idea as when we went from base 10 to base 2, is we draw out or write out what the columns are worth until we get to a number that's bigger than this one. Okay, so 16 to the 0, which is 1s, 16 to the 1, which is 16s, 16 squared, which is 256s, 16 cubed, which is the 4,096s, and then 16 to the 4th. Now, 16 to the 4th power is 65,000 something. It's like 65,536 or something. Will somebody do 4,096 times 16?
65,536.
Yeah, 65,536. So if you do 16 to the 4th, or just 4,096 times 16, you should get 65,536. So 65,536 is bigger than this base 10 number, so that would have value 0. Okay, so really we start here. So we got to determine how many 4,096s are in 60,076. Now I know it's more than 10, right? Because 10 times 4,096 is 40,960. Does anyone got a calculator? If you divide 4,096 into 60,076, what do you get as a whole number? Probably like 14, I guess, isn't it? Or 15 maybe. Is it 15 point something?
14.6.
So when you take, let's see, we do 60,076 divided by 4,096. What do you get? You get 14 point something?
Yeah, 0.666.
Okay, we don't really care about that. Yeah. But 14, so that means we got 14 4,096s and 60,076. So what's 14 in hexadecimal?
E.
E, right? So this would be an E. All right, so then we would subtract. You have 60,076. We're going to subtract 14,000 times 4,096. So what is 14 times 4,096?
This is why modular is so helpful. And there the 57,344.
Say that again.
57,344.
Okay, yeah, we did that earlier. Okay, so now we got to subtract that. So what? It's going to be 2,006 or no, 2,000. 2,000. Now let's see. You get 60. It'd be 656 plus 76. 656. My mind was on, but it's like 730 something.
732.
730 what? 730. Yeah. So, thank you. All right. Now, how many 256s in 2,732? I know there's more than 10, right? Because 10 would be 2560. There's probably 11. If you take 2,732 and divide it by 256, what whole number do we get? It's 10 point something? Oh, okay. So it's 10 point something. So what's 10 in hexadecimal? A. So this would be A. So now we take 2732 minus 10 times 256. That's 2560. So this is going to be what? 172? 172. All right. So how many 16s in 172? Probably 10, right? 10. Yeah. So this is A again, because that would give us 160. And then there's 12 ones and 12. Yeah, and 12 is C. Oh, look at that. It comes out to all letters. Yeah. Yeah. E-A-A-A-C. Okay. So 60,076 is E-A-A-A-C in hexadecimal. Any questions on that? So if you understood what we just went through, these different conversions that we've done, you should be able to convert any base into base 10. For example, well, first, before I give you this next example, any questions on this? Everybody's good up to this point? What if I, or someone, not necessarily me, but what if somebody wanted to know, well, let's do base 5 to base 10. Just as an example of some other base other than these popular bases. Again, these are the bases to worry about, particularly base 2 and base 16. But just to show you that what you just learned would work for any base. Give me a base 5 number, just a few characters. 4421. 4421. And then let's put a radix point, let's put like 3. Okay, so is there 5 in base 5? No. Okay, again, 0 counts as a character. All right, but it's the same idea as we've been doing. This is the 5 to the zeros column, so the 1s. This is 5 to the 1s, so the 5s. This is the 5 to the squared column, so the 25s column. And this is 5 cubed, which is 105. And then this would be the 1/5 column. All right, and then you just go through the same process we've gone through. You'd have 4 times 125, which is 500. We'd have 4 times 25, which is 100. We'd have 2 times 5, which is 10. And then we'd have 1 times 1, which is 1. And then we'd have 3 times a fifth, which is 3/5. Right, and then you just add them up. So this would be what? 611.6 in base 10. If I did everything right here. Okay, does everybody agree? I didn't make any mistakes this time. Okay, so you ready to get crazy?
Oh, yeah.
Because now we're
Oh,
gonna get
yeah.
crazy. And this is gonna show you, hopefully this is gonna show you the importance of hexadecimal when it comes to what we're doing here. So what we're gonna do next is we're gonna go from base 2 directly. I'll explain what I mean by directly in a moment. But we're gonna go from base 2 to base 16 directly. And what I mean by directly is we're not gonna go through base 10, right? Because one way you could do this is you could go from base 2 to base 10, like we did earlier. And then you could go from base 10 to base 16, like we did earlier, right? You could do this in 2 steps. But I'm gonna show you how you can do this in 1 step. And this method is called, for lack of a better name, I don't know if this is official, but this is what I call it. This is called grouping bits. What I'm about to show you. Okay? And this grouping of bits, it's all based on that 2 to the 4 is equal to 16. So give me a binary number and make it a lot of bits.
0, 1, 1, 0, 1, 1, 1, 0, 1,
More bits.
1,
More.
0, 0, 0, 1, 3, explain one. 0, 0.
All right, I think that's good. All right, so how many bits we got here? We got 2, 4, 6, 8, 10, 12, 14, 16, 17 bits. Okay, this is a base 2 number. So if you were gonna take this and go to base 10, I mean, you know, there's quite a few ones here. You need quite a bit of work to do, okay? But you see what you can do instead, you go directly from base 2 to base 16. And again, it's based on this 2 to the 4 equal to 16, starting with the least significant bit. Okay, here's another term. Acronym LSB, and LSB stands for least significant bit. That's always the bit with the smallest value, right? So it's going to be the bit that's furthest to the right. Okay, and then the bit that's furthest to the left, that's called the MSB, which is most significant bit. Okay, so those are just terms you're always going to hear. Okay, so starting with the least significant bit, to go directly from base 2 to base 16, you start grouping in 4s. So here's a 4 grouping. Here's a 4 grouping. Here's a 4 grouping. And then here's a 4 grouping. And let's make this a 1 over here. Okay, I'm adding a bit over here because, see, you start making the 4 groupings with the least significant bit, like you see. Now, if I get to the end here where the most significant bit is, so now the most significant bit would be this bit. Well, I still would take this as a 4 grouping. I would put imaginary zeros here, right? Because if I put imaginary zeros to the left, it doesn't change the value, right? Okay, all right, but after you have grouped the bits in 4s, now you write each 4-bit group as a hexadecimal character. So you see, we take this as a 4-bit binary 1, 1, 0, 0. So this would be the 1s column, this would be the 2s, this would be the 4s, this would be the 8s. So 1, 1, 0, 0 in base 2, what is that in base 16? What character is that? Well, first of all, 1, 1, 0, 0, what is that in base 10? We have no 1s, no 2s, we have a 4, we have an 8. 12. And what's 12 in hexadecimal? C. So I would write that 4-bit grouping as a C. And I do the same thing for all the other 4-bit groupings. See, I treat this as a 4-bit binary number, where again, this is the 1s, this is the 2s, this is the 4s, this is the 8s. So you see, this would be an 8. And I keep doing the same thing. Now I have 1, 1, 0, 1. So I got a 1, I don't have a 2, I have a 4, I have an 8. So what hexadecimal character would that be? 1, 1, 0, 1. Would be what? D. Right, D, because that's 13, right? 8, 4, 1, 13, and 13 in hex is a D. And then we got the same thing here. Actually, let's change it. Let's put it like this. Yeah. Just so we got something different. Okay, now this 4 grouping, it's 1, 0, 0, 1. 9. That would be a 9. And then here we got 0, 0, because again, we're treating these as like imaginary 0 bits, right? So 0, 0, 1, 0, what would that be? A 2. So 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0 in base 2 is equal to 29D8C in hexadecimal. Right? You see, I didn't go through base 10. I just went directly from binary base 2 to hexadecimal base 16. And the reason it's 4 groupings is because 2 to the 4 is 16. And if you don't believe me, if you don't believe what I just showed you is valid, well, take this binary number, convert it to base 10, you'll get a number. Take this hexadecimal number, convert it to base 10, and you're going to get the same number. It works. And this also shows you why base 16 is popular in the digital world. It's popular because a lot of times you'll have circuitry where your data is many bits. In fact, the follow-on course to this course, okay, CPE 233, in that class, you actually build a microprocessor. And with what we teach you in this class, you're going to use it in that class to build a microprocessor, which is a fairly complex digital devices, you'll learn if you don't already know. And that microprocessor that you build in CP233, it has 32-bit data. So the data that it's using is 32 ones and zeros. So when you want to describe, the data, whatever it might be representing in that microprocessor, do you want to say 32 ones and zeros? Or would you rather say a much smaller number of hexadecimal characters? Because how many hex characters would it take to represent 32 bits? 8, right? Because every 4-bit grouping is 1 hexadecimal character, right? So you just take the number of bits divided by 4. So instead of saying 32 ones and zeros, you can just say 8 hexadecimal characters. So you see, that's really the power of base 16 when it comes to digital circuitry, is you can say a great amount of data in less characters, right? A fourth as many. Okay. Okay, well, this works the other way too. Like, say you started out with a hexadecimal character like A39B, let's say. And I want to go directly from base 16 to base 2. Well, I can do this in reverse. I can write each hexadecimal character as a 4-bit binary number. So you see, I would take B and write it as a 4-bit binary. So what's B in binary? 11. Okay, it's 11, but how would you write it in binary? 11. Oh, right, 1, 0, 1, 1, right? Because remember, this is the ones column, 2s, 4s, 8s. So 11, I have an 8, I have a 2, I have a 1. Right? I don't have any 4s. Okay, how about 9? 9, 0, 0, 1. 1, 0, 0, 1, yep. How about 3? 0, 0, 1, 1. 0, 0, 1, 1. And how about A? 1, 0, 1. Yep, 1, 0, 1, 0. So you see, A39B and hex is equal to 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1 in these two. Right? But it's much easier to say this than that. Right?
Does it matter if you don't start thinking about it? If you start from the left-hand side of the group, it's a thing.
Oh, you're saying like if there's a decimal? Yeah, if there's a decimal, like say there was, like an 8 here. I mean, you would just put a decimal and then write that as 8. And then same sort of thing, if in your base 2 number, you had a radix with some over here, you would just take those 4 and, write it as a hexadecimal character. So it works on
even number.
Say that again?
It's always going to be an even number, like 4s.
Yeah, the grouping, if you're going from base 2 to base 16 or the other way, the groupings of the binary have to be 4. And again, that's based on this. Now, your question brings up another question that I could ask you, right? Because even though we don't deal with octal that much, can you think about how we would group binary to go directly from binary to octal? In 3s, right? Because 2 to the 3 is 8. So if you had a binary number and you wanted to go directly to octal, you would make groupings of 3 and write each grouping of 3 as that octal character. Yeah. Yeah, but again, the one to worry about in this class, and also the one that you're going to use the most often in any digital class you take, is this when you go in base 2 to base 16.
We think you're missing a 0 for ratio.
Oh, did I screw up here? Let's see, this is 11 here. Yeah, I probably was going too fast. And yeah, thank you. There should be a 0. Yeah. Hey, I'm being serious, where I'm not trying to do this on purpose. But yeah, thank you. Yeah, that's important because that would change the whole value. So. Okay. All righty. So I think that's what I wanted to cover. Let's see. Anything I missed here? No, that's all I wanted to do for the lecture. So you can see it took a little bit more. Well, actually, a little less than an hour. It's like 55 minutes or so. So the next thing, you can take a break before you start this. But the next thing, because we're done with lecture today, the next thing is to do the activity. So on each table, there should be an activity for everyone. If you don't have one, let me know. I have extras. So you want to go ahead and do that activity. Again, each student do their own work, but you can help each other. You can ask me questions. The answers, I'm gonna put the answers right here on this table, and you know, you can come up and take a picture with your phone if you want. Okay, don't take the paper though. Okay, everyone needs that. Yeah, so work on that, help each other. If you have questions, ask me questions. And when your table is done, you just turn in one per table. Okay, and it's up to you how you want to turn it in. Like what some groups do is, you know, they'll each do their own thing, and then they'll look at each person's work and they'll choose one to turn in for the group. Okay, other people, they do some sort of like combination, like, you know, one person does two problems, another person does two problems, and they combine them. Okay, but make sure you do all the problems yourself, but how you turn it in, you know, that's up to you. You have a question? Yeah. So if you, look, if you work on a tablet, you should be able to print out. You have to. Well, I think I have a table, so if you can't connect to it. Yeah, sure. Yeah, and then when you do turn in your activity, make sure everybody's name is on it, and also put the group number. I'll get your question in a minute. This is group 1. Group 2, okay, nobody's at table 3, so no group 3. You're group 4, 5, 6, 7, 8. How many people know what an integrated circuit is? Not too many people know what an IC is. Okay, well, what you're gonna learn. Okay, I used to teach circuits, so I like talking about circuits. So this isn't part of the class, but you know, this is stuff that's good to know. When you have an IC, it's usually a rectangle thing like this, and there'll be like what's called a keyway, which is a little U, or there'll be a dot. And where the dot is, that's pin 1. And then let's say it's an 8-pin IC, although this applies to any number of pins. See, the way the pins go in an IC is that wherever the identifier is, whether it's a keyway, which is this U, or a dot, like this black dot here, 1 is next to the identifier, and then it goes 2, 3, 4, 5, 6, 7, 8, like wraps around. So just imagine these tables being like an IC, and the keyway up there. That's like pin 1, group 1, pin 2, group 2, pin 3, pin 4, pin 5. Never thought tables could help you with integrated circuits, did you?
Plan this out.
Well, that helps me remember. Like, I just think that way. I just think, oh, this is like an IC, that's pin 1.
I love it. That was like that's supposed to be an op amp, sorry.
Well, yeah, they do have op-amp chips that are.
Okay, it's just gonna look like an op amp, so it's like, so.
Yeah, I mean, that's a popular op-amp chip, yeah.
Okay.
You'll use it in your analog classes. Well, there's different ones, but the one I think they use is a 741. It's an old one. I mean, that's as old as I am. Yeah, old it is.
I think I used one in before, so that's cool.
What's that? You said what?
I was just saying, I've used the op amp before, so it's pretty.
Yeah, but they do have op-amp chips that have more pins. Like you can buy like 16 pins, and there's multiple op-amps inside.
Oh, cool.
Like they have ICs that have like 4 op-amps inside.
Will not use ICs at all for logic, or are we just gonna do it on the
Oh, great question. Actually, I'm gonna answer that question after the activity, because I'm gonna talk a little bit about the lab and. Yeah, because, I mean, real quick, in the old days, it was done like that.
Yeah.
Like, no, back when I was an undergrad, we used to have breadboards with the ICs with it. But you see, now it's done with software, and that gets into what you're gonna be doing in the lab.
Yeah.
So, yeah. Also, I just want to let you know that you might see me looking at myself in this mirror. And I just want you to know, it's not like I'm vain or anything. It's just I woke up with this red eye. Can you see that my eye is red?
Not really.
Oh, you can't really see. Oh, maybe the drops help. it helped a little bit. But anyway, I woke up with this red eye. And I put some eye drops in it earlier this morning and it got redder. After I took the drops, but it looks like it's worked a little bit better. But anyway, if you see me looking at myself, it's not because I'm vain. It's because I'm looking at
He's just doing what he steal them. It's working on Magnum. What's up?
It's wonderful.
So while I was lecturing, did Kate show up? Is Kate here? Oh, I guess Kate's not here. Okay, just wanted to make sure.
Defining technique.